Okay, so I'm going to be presenting a model for semantic localization. Again, my name is Matt Weber. I'm at the University of California, Berkeley, working with Edward Lee. So I'm going to be talking about a model for semantic localization, and I'll start by talking about my big assumption, which is also my motivation, which is that indoor localization is a hard problem, and that there has not yet been a dominant solution to indoor localization, and it may be the case that no one single solution even exists. Because different applications have different requirements for location information, different systems perform differently in different indoor environments, for a number of other reasons like at cost too. So what's valuable is a method to combine information that's known in different systems and to be able to infer stuff from stuff that's known partially in one system and known in another one. So this project, which is very much a work in progress, is an attempt to make that happen. So I'll start off by talking about the semantics of the swarm. I'll move on to a mapping formalism. Then I'll show how you can apply the formalism to infer other things logically about what's going on in the real world. And I'll finish up with some of the ways you could use this. So semantics of the swarm. This slide is a little old because it has the words universal data plane, which has since been renamed global data plane. But the key idea here is that the global data plane is going to be able to make it possible for processes to live in the swarm and not be attached to a particular machine. So these persistent processes are going to need to be interacting with each other. They're going to need to be interacting with real-world context, with input, with sensors, with actuators. And they live in this flat universal address space, which then is just a data plane. And each of these machines is running on top of an underlying system too, and that matters. So there's information that is available to individual entities in the process plane, as I'm going to call it, which are not available to other entities. If a button is pressed on a particular machine, that is known locally, not everywhere at once. So you can sort of visualize it like this. By the way, this is a work primarily done by Chris Shaver and Martin Lostra. I want to give credit where credit's due. So the idea here is that we want abstraction, which is able to represent a process that can create a new process. It can remember connections to other processes that it knows about, and it can also send messages. So we have this basically evolving graph of what we're calling reactors, which will allow you to do computation in the swarm. So a reactor basically consists of a reaction rule, or it's a series of reaction rules. Or the part of a reactor that determines what gets done consists of a series of reaction rules, which are predicated by a condition, which is a logical statement. And when this condition is met, it causes an action to happen, and then it's able to rewrite some or multiples of its reaction rules. This is a model of computation which is useful for handling these events that are going to be triggered by real-world context. But they can also be handled by internal message passing too, as well as external stuff. So the point of this, in terms of the rest of my talk, is going to be that these conditions, particularly the context-relevant ones, are things that I can address. I'm leaving the other aspects of this to the other guys working on this project.
So one quick question, is this like guarded commands, except that reactions allow you to do rule rewriting, whereas guarded commands don't usually do that?
Yeah. So this is a full-blown model of computation, which would allow you to evolve the system over time.
Okay.
So the format for these conditions is a first-order language. A first-order language consists of relations. It consists of conjunctions, disjunctions, quantifiers, and the equality comparison operator. So if we wanted to describe, we wanted to look for strawberry ice cream. The way we could formulate this as one of these conditions would be to say, would be like this. So there exists an X, which is ice cream. It's pink. It's frozen. I'm near it, and it's inside something, and I want to know what that something is. So y is now a free variable, which could be evaluated for the actual location of this ice cream. basically, there are two ways you can interpret these conditions. One is to tell when something has happened. The other is to basically look up stuff. So this is a format of sort of the first case, because we want to look up what the ice cream is contained by. And this would then allow us to trigger the reaction when we find it. So each of these relations here is encapsulating the idea of a phenomenon. The definition of phenomenon is an observable occurrence. So these are real-world things that are happening, which we're modeling as relations. So some very basic model theory here is that a first-order language sentence like this means nothing on its own. Well, it means something, but you can't tell if it's true or not. You need some kind of model to evaluate it. So a context model goes on the left side here, and this symbol, which is called the double turnstile, means that this models this, which means that this is true in this model. So if it so happens that the ice cream is in an ice cream cooler, and this ice cream cooler is part of the context model, then this would evaluate to true. So again, the part of this that I can handle is the bottom part, which deals with the location-relevant context. So here's an example of a map which would work as the model for the sentence. So if I'm over here, this, by the way, is the DLP Center in Berkeley, which is my lab area. So if I'm over here, and the ice cream is in an ice cream cooler here in the lounge, then this evaluates a true, because the contains relation is valid for this in this model. It's also valid for this. So the ice cream is both in the lounge and it's also in the ice cream cooler. However, if we moved the cooler over here with the ice cream, then this would no longer be valid. This would no longer be true because we have broken the proximity relation. So there are a variety of phenomena that are useful in localization, and this is a list of some of them. So angle and orientation matter, as do distance and proximity, path, line of sight, and containment too. But again, this is not meant to be an exhaustive list. I'll be saying more about each of these in a little bit. Just to be clear about what I mean by proximity, that means that we can bound the distance by some amount. So proximity of 20 meters means you're within at least 20 meters of the thing you're looking for. So when it comes to representations of the models, there are two distinct categories of models that I've been thinking about. So the first kind is the kind on the left, the physical maps. And these are somewhat more conventional, at least this kind of physical map, a floor plan, is very conventional. And on the right, this would fall more under the idea of semantic localization, would be a phenomenal map, which describes the way that different entities in the space relate to each other. So if we were interested in answering questions about what stuff is contained by other stuff, a physical map like this is one way you could represent that. You can also just simply convert the relations into a graph, because you can always convert a relation into a graph. Just put a directed edge where you have the relation. We could also use this phenomenal map too to evaluate the same kinds of context requirements for reactors. So I'll be saying more about what this kind of structure is saying later. But first, physical maps. This is an image from Wikipedia which describes the idea of different kinds of mathematical spaces. Basically, the Euclidean space that we all know and love is an inner product space, which fits inside this little bubble. But there are other spaces too, which you can think of as generalizations on the internal spaces. So a metric space an inner product space is a metric space, but metric space is more general. It doesn't have the same requirements that inner product space does. And same with the topological space. I'd also just wrap the outside of this with one more layer, which it would just be to say it's a set with no implied structure at all. This is not an exhaustive list of the kinds of physical maps that you could have, but again, this is just a sample of what you might see. So for the next couple slides, I'll talk about how different types of physical maps might arise from different kinds of sensors, and the kinds of structure that each of these spaces has. So to start with a set is basically just a domain, and we don't require anything about it besides it to just be a set. An example of a localization system that would do this is classic Foursquare. Foursquare is now moving on to doing real localization where they can tell you where you are, you don't have to check in. But classic Foursquare meant that you were just saying, I'm at this location. And you don't need to have any kind of significant map of the world in order to make this work. You just have to know what the things are that you could be potentially at. So this is an example of a set. A topological space is a kind of funky mathematical space because it allows you to do things like this and consider it to be the same space. So you can continuously deform sections of the space, and you haven't changed the space. There's a joke that this is supposed to be about here, which is that a topologist can't tell the difference between a coffee cup and a donut because they're topologically the same. Similarly, if we're interested in paths, we can continuously deform this path at the top to the one on the bottom, which means from a topological perspective, they're, again, the same path. A topological space doesn't have any notion of distance, just continuity. So the way we define a topology is with a set and a set of open sets. And there's a definition for continuity that works in open sets that stitches this all together. So how could this be relevant? Well, you can build a topological map by looking at the adjacency of different zones on like a floor plan. Or you could also look at lines of sight and see where it's possible to move. Because if you're moving in the same direction without going around any obstacles or going down a different hallway, then those should be equivalent paths in the topological spaces mindset, just like this was. Moving inner in our onion of spaces, metric spaces. So metric spaces are, they have an idea of distance and not much else. So we have a space, which is this domain, and a function that maps elements of the domain to a real number, which generalizes the concept of distance. So we require a few things about this metric to make it count as a valid metric. One is that if 2 points are the same point, if and only if that, then their distance metric has to evaluate to 0. But we don't need to have a vector space for this to work. So we don't need to have a way to add or subtract different elements of the space. So an example where this could be relevant is if you wanted to get rid of the Euclidean distance space, for some example, where it's not really appropriate. So let's say you had a long hallway. Let's say it's like this. So there's a long hallway going over here, and then you go down a corner, you make another turn, and you come back this way. And you want to see what the distance is between this point and this point. If you looked at Euclidean distance, you'd get that they were very close together. But in terms of the actually useful metric here, which is how long would it take a person to go from here to here, what we want is to know how long it would take to walk from this point to this point. So a way you could define the metric for this is to say that if a point is part of a barrier, all other points have an infinite distance to it. Otherwise, the distance is the minimum length continuous path from those 2 points. And because this infinity introduces discontinuities, that means that you have to go around obstacles. So a way that you could conceivably build this, actually I was thinking this might be relevant to whereabouts, because if you have a bunch of places, you don't know where those places are, and you have the duration and time it takes for people to walk from one to the other, and you make some assumption about how fast people are moving, you can build, or you can sort of learn what the minimum time it takes people to move from one to the other, and consequently the minimum path distance. Finally, we have an inner product space, which is more general than Euclidean spaces, but generally when I talk about this, I mean Euclidean spaces. So the advantage of an inner product, so one thing, this is a vector space. So in addition to just having a field of our domain, we also have vector space, which means we can add and subtract points. But the part of this that is relevant for my purposes here is this inner product, which allows us to have an idea of angles. So none of those other spaces I talked about before have a concept of an angle. So to bring this all together, this is the formalism that I'll use for the rest of this when talking about spaces. So a space consists of a domain and a structure. It's a tuple of domain and structure. Structure is kind of a loose way to describe whatever is on the right after this. We also have time, which is a partially ordered set. So a partially ordered set could be a total order, like real numbers or integers, but I want to allow for the possibility that we want to order things by external events. I know that Ruzba had a particularly cool demo at the Terraform conference where he was able to detect high fives, and that way he could synchronize clocks by determining when this event happened. So I want to allow for that to be the model of time as well. The idea of an entity is a subset of the domain. So to give you an idea of this, if your domain is with a floor plan, an entity could be a room in that floor plan. An entity could be a person or a point in that floor plan. So a localization function from one space to another space maps an entity and a time to an entity in the other space. I'll have an example of this in just a bit. Finally, a map is a space that's localized with meaningful entities. So here's an example of this approach, which may seem to be overly complicated for just saying we're putting stuff at a place. But you'll see that this kind of definition is actually general and lets you do some interesting things. So getting back to our ice cream example, let's say that we start with one space, which is a set. I'm calling this a label space, which is basically a set with no structure to it. It's just a bunch of stuff. So there's me, there's the cooler, there's the lounge. There are a bunch of different rooms. These are all, so any subset of this is an entity in this label space. But we're probably not going to be interested in the union of me and the cooler. We might, but we probably won't. So let's say we want to map this onto a floor plan. So the floor plan is a two-dimensional Euclidean space, hence the E squared notation. And time is just going to be real numbers starting at zero. So our localization function here is going to map from entities here to entities in this space, which results in this floor plan. So I just made up some coordinates that correspond to where these things might be. So the location of me at 5 o'clock p.m., because time, I forgot to mention this, so time is necessary for a lot of these relations to make sense, because just saying, like, in the library is extremely vague, and you can't really trigger any kind of meaningful events off of that. What you should say is in the library at this time. So that's why I have 5 p.m. for all of these. But anyway, so the location of me is a single point, which is at this coordinate. The location of the cooler is also a single point, which is at this coordinate. The location of the lounge is actually a larger subset. It's not just a point, it's actually a range. So we can go from 28 to 32 and 12 to 18, and we're still in the lounge. So what's cool about this is that the cooler wound up being a subset of the lounge. And that's actually exactly what we want, because when something is inside something else in this representation, it's going to be a subset of that other thing. So we can actually define formally the idea of being inside a space as being a subset, one entity being a subset of another entity. So because of this property, we can say that together this map, these two spaces and localization function, model this contains relationship for the cooler being inside the lounge. Here's a second example, which is getting at topological spaces. So remember that in this kind of map, distance is completely irrelevant. We just care about continuity. So what this map was created through was by looking at the different landmark points that you could see from a particular observation. So if you were at this red square, you could see these corners of the space. Now, it just so happens that the way the authors of this paper chose to represent this topological map are completely consistent in terms of Euclidean space with where they are in the in this diagram, but the topology doesn't actually have a notion of coordinates. So there's like no real way to talk about this being this particular formation. It's just like an abstract blob, which is just being represented this way. So how does this relate to the model that I was talking about before? Well, what we can do is we can map a simplex, which is one of these blobs over here, to a region of space. So what that means is that we can say that if you are somewhere here, not actually on one of these landmark points, you have the same topological path possibilities as you would if you were here. So we are mapping this simplex to a convex hull of these points in the Euclidean space. This is a bit more abstract, and I can talk about this with any of you later if you're a little confused by it. So moving on to phenomenal maps, there's a correspondence between physical maps and phenomenal maps. And there's a very basic one going in this direction, which is that if a physical map is capable of answering a question about a phenomenon, we can just read it off of the map. So if we have a Euclidean space, we can read angle and orientation off of that, distance, paths, contains, all of that. If we have a metric space, we can't read angle and orientation. If we have topological space, we can't read either of these two, and with a set, we can't do any of these three. And then we can also go in the opposite direction. So we can actually construct physical maps or a family of physical maps from phenomena. So a classic example of this would be using angles and distance to do triangulation. So a property of this is that this isn't actually going to give us one particular Euclidean space. It's going to give us a set of Euclidean spaces that correspond to the different ways that you could put these points down in a space and preserve the distance. So if you rotate your set of points that you're trying to localize, that's equally going to be valid as a phenomenal representation. It's equally going to give you the same phenomenal representations, which is why we get a family of physical maps. So what's cool about physical maps, or phenomenal maps too, is that we can do inference on them. Because we know that they map onto these physical spaces, we can then learn new things about these phenomenal maps. So if we take a phenomenal map, we construct its family, or we just look at what kind of space it's in, then we can derive new facts. So for this next section here, I'm doing a little shortcut notation. What I should do is this, where I say that we're localizing this label to a point in domain B, not A. But just as shorthand for that, I'm going to say that what the DOP center is in the in space B is just going to be the bubble. So I'm cheating a little. So here's something you can do with sets. So if we know the contains relation between two entities, which is modeled by this black arrow, we can have a hierarchy of stuff being inside other stuff. If we know that the DOP center lounge is inside the DOP center, and we know the DOP center microwave is inside the DOP center lounge, then because of transitivity for subsets, we know that the DOP center microwave is inside the DOP center. And this is kind of an obvious example here, but you can imagine that you could have a much more complicated graph, and being able to do this automatically as a rule is very valuable. Another possible set relation here is this dotted line, which means that these two spaces are disjoint. They have no points in common. And you can do another inference rule here with these disjoint spaces by saying that if a set is disjoint from a parent of another one, it's going to be disjoint from a child of that first one. So the idea of these maps is that they're going to present partial information about the world. We may not know everything, we may not be able to put everything into one of these maps, but we want to be able to establish things that are known. So what we want is to have the edges represent known true facts, and if something isn't represented as an edge, it doesn't mean it's false, that just means that we don't know it yet. So you can't prove things by contradiction here, you can just prove things by construction. So another example, this one I think is really interesting because this is an incredibly practical localization method. So let's say that you wanted to, this is basically whereabouts. If you wanted to detect proximity to stuff and you had a bound on the radius that you were able to detect something, you can establish proximity of two devices if they are within, so if you detect one within the range of another, you can establish proximity within that radius, which means that your distance is less than that radius. These are undirected arrows because proximity is reflexive. So let's say we have this system here where B is within A and C is near B, and we have different distances here. So we can actually apply the triangle inequality, which we can do because this is in a metric space. And we can derive the fact that A and C are within 40 meters of each other. It's also true that they're within 60 meters of each other, but 40 meters is a more descriptive thing to say. We also want to talk about the possibility that two things are not within range of each other. So we can represent that with basically an anti-proximity measurement here, which is the dotted line. And for that, we mean that they're greater than that distance from each other. If you're really sure that your sensing system is going to work, and you'll detect something if it is within range, you can establish anti-proximity just by knowing that you're not picking up the signal. So if we apply the contrapositive of the triangle inequality, we can establish that if A and C have anti-proximity of 10 meters from each other, then either this edge exists or this edge exists. And what you can imagine doing with a sufficiently large network of this is getting upper and lower bounds on the distance of things from each other. So just not even looking at this inferred edge, just if we look at this, we can tell from this graph that A and C are at least they're at least within 40 meters of each other, but their distance is greater than 10 meters of each other. And with enough things, you could imagine squeezing down the distance of everything from everything else to get an accurate distance measurement just from this binary sensing relationship. I'll skip this in the interest of time. So for inner product spaces, we can do triangulation, trilateration. One example for how you might want to do this with phenomena would be to do iterative trilateration. So if we have distance measurements from 3 points, we can establish the distance of a new point like this, and then we can establish the distance of a new point building off of what we learned before. We couldn't have localized f if we hadn't first localized e, because f doesn't have a connection to anything else. So this allows us to build up new distances without ever actually having to construct a specific physical map. Another cool thing that we can do is we can use the inner product that these spaces have to establish rigidity measurements. Basically, the idea here is that if we have this structure of distances, we can, and let's say we have a bogus distance measurement here that's twice as long as it appears that it actually is. We can tell that this shape doesn't make sense in Euclidean space. There's no way to draw that kind of shape in Euclidean space because this point is required to be here by all the other connections, and this distance is saying it needs to be out here. So if we do a rigidity check through their approach, we can tell that this edge was actually incorrect. This is another kind of inference that we could do with a phenomenal map. So if phenomenal maps are so great, do we even need physical maps at all? I think that's a legitimate question to ask. And if you actually did have a complete phenomenal map of everything that you might ever want to ask, then I agree. There's really no reason that you would want to have a physical map. But this isn't A, likely to happen, and B, I'm not sure if it's possible. I think mathematically it's not possible to be able to establish everything here. And at the very least, if you did, it would be an inefficient representation of your knowledge. Because looking back at this distance measurement thing, if we had a complete phenomenal map which had pairwise distances between everything, that would be pointless because you can construct a physical map out of just having 3 edges connected to everything else using this trilateration method. And then you could just read off the distance measurements from the physical map. So it's actually not even efficient in terms of representing the space, representing this information to use the physical map here. Also, you lose out on the ability to do what I'm going to talk about doing next, which is now the kind of inference you can do using physical maps. So this has to do with doing inference on our localization functions. So let's start by saying that, again, this is partial information, and a localization function may be a partial function that might not be defined for all entities. And we may not even have a localization function at all between 2 different spaces. So given partial information, what can we infer? A straightforward example of this is if we have a localization function from space 1 to space 2 and one from space 2 to space 3, we can infer from this that we do in fact have a localization function from 1 to 3 that we can construct just by composing these functions. So first, we apply this function to an ND in S1, then we apply this function to what we get out of that, and we wind up with something in S3. So now we are able to determine a correspondence between maps just by looking at 2 other ones. This also gets complicated when we want to do inference with common entities. So if we have entities in S1 that are mapped onto S2 and entities in S1 that are mapped onto S3, some of the time we can establish a mapping from S2 to S3. Like that. And an example of this would be if we had 2 Euclidean maps. So it turns out that if you have 3 points in common on 2 Euclidean maps, you're able to uniquely establish the correspondence between the 2 maps. So I've drawn arrows between each of the stars, but I also drew an angle here to represent the fact that this is actually a total function. Now we can now take any arbitrary point in this space and map it onto here just because of the correspondence we have in the localization functions up here. So we can infer something in this direction by doing that. Another example here would be, let's say we had a metric space, which is very hard to draw. So I didn't do that. But let's say that we had 2 points between where we had a distance of 27. Let's say that in this Euclidean space, we knew that the diameter, the maximum distance from one point to another, was 27. What that means is that points A and B need to be on the extreme points, here and here. We're not sure which one is which, but we've now eliminated the possibilities for A and B's location from literally an infinite number of possibilities to just 2. So this is a powerful thing that you could try to do. Okay, so nearing the end here.
Yeah, you have maybe I don't know, is there people out there?
Okay, well,
Gathering. They are.
Yeah,
okay, this is the last couple slides, so good. This should work out just perfectly. So, so what we want to be able to do is establish heterogeneous composition of space models. So you have one localization system over here and another over there. They don't even talk the same language. We want to be able to fix that problem. This also would allow us to structure the event language for reactors, like I mentioned earlier. Something else that I think is potentially really cool is that using this model, you can determine things about privacy, and you can actually prove things about privacy regarding location. So one case that's kind of extreme would be to decide not to share anything from an inner space with an outer space. Another opportunity would be to say what's going on in the inner space, but don't say where this inner space is in relation to the outside world. Finally, this is probably the most interesting one, where we could use the inference rules to determine what it's possible for someone else to learn about your inner space given the localization function and some phenomenal observations that you give them. So you can actually determine if you're revealing your secret location by exposing too many answers to probing questions. So the reason that I'm here, I guess it's kind of funny to bring this up at the end, is I want to see how the localization systems that this group is working on fit into this model. And I think that combining all of them on top of each other in the way that I proposed here could be a really interesting prospect in the future. So other questions are to determine practical data representations for this, because what I've given here is the kind of abstract problem and formulation that you were making fun of earlier.
I wasn't making fun of
No,
it.
it's okay.
I'm just saying it's very hard if you're not grounding it in an actual
Right.
application to kind of.
And that's what I'm hoping to do
Test it,
here
yeah.
at the top. And finally, and this is extremely important, I haven't addressed it at all, how does probability fit into this model? I'm assuming so far that we actually are able to establish facts about the world, but this all just breaks down once you start introducing probability, which should be very important. So to conclude, it's very important to establish formal semantics for this form, because if we don't have those, we can't say anything concrete about what it's doing. We can't determine if we can meet performance agreements. We can't determine if we're violating security or privacy. We don't have anything. We don't have semantics. Or we have something. We have potentially broken system. So what I'm giving in this presentation is a formalism for doing inference on context related to location. And this is applications to privacy and the composability of localization systems. So that's it.
Yay, thank you.
Yeah.
Yay.